So I have a question about the interpretations of quantum mechanics.
Yeah.
There's plenty of hubbub about interpretations of quantum mechanics. But if it's already understood that the greater theory, the more fundamental theory will be a theory of quantum gravity, furthermore, that the only or the most well-developed UV complete non-perturbative approach is string theory, then why isn't there more work done on the quote-unquote interpretations of string theory?
Yeah, so I would recommend that people look up the work of Nick Huggett, for example, a philosopher of physics who's given a lot of attention to trying to understand the philosophy, the metaphysics and philosophical questions surrounding string theory. I did some work with some of my colleagues, some preliminary work on string theory. We just had a lot of other things we were working on, and we got pulled away from this. I think partly the reason there's been less philosophical work on string theory is because it's just newer than things like relativity and quantum mechanics. You know, relativity goes back over 100 years. Quantum theory goes back over 100 years. So there's just been a lot more time for people to think about these theories. String theory is of much more recent vintage. I think one issue is that string theory is still very speculative. We don't know that string theory is the confirmed best theory of quantum gravity. And I think that there's some reluctance to try to spend too much time trying to understand the metaphysical underpinnings of a theory that isn't substantially verified at this point. We don't have any real empirical confirmation of string theory at this point. I said before that philosophers of physics like to understand the mathematical structure and features and implicit assumptions and everything for our best, most successful physical theories. And by this, I mean theories that have proved the test of time, that have been empirically verified. Because the work that we do for those theories, we feel will stand the test of time. Whereas if you're working on trying to understand the philosophical underpinnings of a speculative theory that might not last, well, then your work on that might also not last. Now, of course, one could take the view that philosophical work, foundational work on string theory, may help move quantum gravity forward. And I think that may be partly what inspires people to think about these questions. But I would recommend that you interview some of the people who work on the philosophy of string theory. I think Nick Huggett would be an excellent person for you to talk with. I think you might get some insight, and you could ask him what motivates him to work on this theory. I think the other main reason why fewer people in philosophy and foundations of physics work on string theory is that string theory is mathematically very complicated. I worked in string theory during my during graduate school, and there are very beautiful features of string theory. I mean, you work on it and you see beautiful connections. It changes how you think about quantum field theory in really profound ways. I learned a lot about quantum field theory from learning string theory.
Right.
But it is a very mathematically intricate theory, and I think that presents an obstacle for a larger fraction of people working in philosophy of physics to work on it. Now, the people I know working in philosophy of physics are very mathematically sophisticated, but there's an investment in time that one has to make in order to be able to work on string theory. A bigger investment in time, I think, than maybe the case for other theories people can work on. And so I think that's been a hindrance to more people working on it. But there are people who have decided to invest that time and they've worked on it. And it's interesting to know, to think about what they've been able to see. I think one of the difficulties is that because string theory is in many ways still a very partial theory, it's not yet quite ripe enough to be able to start making strong statements about the metaphysics. We have only a very sort of superficial understanding of exactly what the theory entails. And that makes it difficult to ask deep foundational questions about it at this stage of development.
What did you learn about QFT from string theory that isn't string contingent?
Oh, that isn't string contingent. That's a good question. I mean, so one thing I learned about quantum field theories from string theory is how to think about gauge theories. I'm a little worried that if I get in the weeds here, this is going to become technical very quickly.
Oh, the audience loves the technicality. Don't worry.
Okay. Well, so in string theory, one models the kinds of particles that transmit forces using certain kinds of strings. We use open strings to model gauge theories, and we use closed strings to model gravitons. And the actual force carriers correspond to particular quantized excitations of these strings. One question you could ask is, well, if I have a particular, quantized excited mode of a particular kind of a string, and this string is supposed to describe some kind of force carrier, well, I've got the particles, but how do I understand where the field comes from and the structure of the field? Why should these fields have certain features? Why should gauge fields exhibit gauge invariance? Why should the gravitational field exhibit diffeomorphism invariance and the equivalence principle? Why should it treat inertial and gravitational mass as being similar kinds of things in the first place? And in string theory, because you're working in a so-called first quantized formalism most of the time, you're working with individual strings, which manifest as individual particles, rather than in the so-called second quantized formalism that's called string field theory, which is its own discipline, and there are people who work in string field theory. But a lot of the time, you're working in the first quantized string particles as sort of individual excitations of these strings. Understanding how you get all the intricate, rich structures that show up in quantum field theory from these strings ports right over to thinking about the relationship between, not in string theory, the particles that correspond to fields and the fields that they're related with. So, for example, photons are associated with the electromagnetic field. The Higgs boson is associated with the Higgs field. The electron is associated with what's called the electron field, which is a fermionic field. It's a very interesting kind of a thing. Quarks have their own fields. Neutrinos have their fields. There's fields associated with all these particles. And understanding the relationship between a field and its corresponding particle is a little bit subtle. One way to think about it is that the field is a sort of prior idea, and that you can argue using some elementary quantum mechanics, thinking of fields as connected systems of harmonic oscillators, that quantum mechanics harmonic oscillators can only be excited in quantized amounts. These fields can only be excited in quantized energetic amounts. And each such quantized excitation, each quantized energetic excitation corresponds to one more quantum, one more particle of that field showing up. This is the sense in which, say, the Higgs boson is one quantized excitation of the underlying Higgs field. But you may also ask the opposite question. If I imagine starting with some statement about the properties of particles, let's suppose I've got a particle with certain features. I've got a particle, it's got this intrinsic inertial mass. It's got this intrinsic charge. It's got this intrinsic spinniness or spin or angular momentum. Can I predict what kind of a field it will correspond to? And can I even, in some sense, model the field as some appropriately defined quantum state involving these particles, as some coherent state of these particles? And if I do that, what kind of field do I get? What features does the field have? And what I took from string theory, which I guess you could have learned just in quantum field theory, but for me, it took learning string theory to see this connection, was that the properties of these particles, again, things like their mass and their charge and their spin and these are the features of these particles, can reveal to you the structure of the fields they correspond to.
Interesting.
For example, the fact that photons have zero intrinsic inertial mass and have 1 unit h-bar of intrinsic spin and have no charge. That you can use to show that the field that emerges from photons is going to look something like the electromagnetic field, and in particular, the masslessness of the photon and its spin being 1 is connected with gauge invariance in this electromagnetic field. So that's the sort of connection. And again, you could understand this connection without string theory. If you pick up Steven Weinberg's books on quantum field theory, he also explores this connection, although in a way that when I first learned it from Steven Weinberg's book, I didn't find as intuitively clear as I did from string theory. So that would be an example, right? And, string theory has generated a number of other spin-offs that people working in quantum gravity spend a lot of their time thinking about, things like holography, to whatever extent that you think that those ideas are worthwhile, they're certainly very interesting. And arguably they stand on their own separately from string theory, at least some of them.
I should have been asking about the interpretations of quantum field theory as well. Who are some people I should be speaking to?
Interpretations of quantum field theory. There's a number of people who work in that area who might be worth speaking to. Michael Miller, who's particularly convenient because he's at the University of Toronto. You might talk to...
Right, we talked about him yesterday?
We did, yes.
Okay.
You might talk to Doreen Fraser, who's at the University of Waterloo. So also not someone who's very far away. You might talk to David Baker, who's given a lot of thought to quantum field theory. He's at University of Michigan.
Well, now
Noel Swanson would be a good person to talk to. He's at University of Delaware. Hans Halvorsen at Princeton University. Both Noel Swanson and Hans Halvorsen work primarily with algebraic quantum field theory. So they'd both be interesting people to talk to about how we think about quantum field theory. So I have a lot of people I would recommend.
Okay. Now that I've accidentally, inadvertently teased the audience about interpretations of QFT, why don't you outline some of them? Why don't you outline two of them?
Right. So quantum field theories live within the umbrella of quantum theory. So you have the same kinds of axioms. You have quantum states in some sense, although depending on how you formulate a quantum field theory, you might prefer to work with what are called C-star algebras. We've talked about that rather than Hilbert spaces, but there's similar conceptual basis for thinking about quantum states and some kind of evolution law and observables being represented by an algebra of, an algebra means a collection of mathematical symbols that are the observables. And you still have to use the Born rule to calculate things probabilistically, or at least compute measurement averages of things. So the basic rules still apply. Some people make a terminological distinction between quantum theory, which is the more general idea, and quantum mechanics, which is specifically about particles. Some people use the word quantum mechanics to mean all of quantum theory, so you have to be very careful what they mean. When I say quantum mechanics, I usually mean quantum theory applied to models of systems of particles. And I use quantum theory to refer to the more general framework, of which quantum mechanics is an example, and quantum field theory is an example, and string theory is an example, right? These are all phrased within this larger formalism of quantum theory. So some of the foundational philosophical, metaphysical, interpretational questions that one considers in quantum theory are still present in quantum field theory. Quantum field theory doesn't let you get around the measurement problem. Most of the time in quantum field theory, you're, practically speaking, if you're doing quantum field theory for practical purposes, for particle accelerator experiments, you're mostly imagining some collection of particles coming in the far past, which for particle physics experiments is not really very far in the past.
Right.
And then you consider some other collection of particles in the far future, again, quote unquote, far future. And you want to compute roughly speaking, the probability to go from one to the other. This is usually phrased in technical terms, in terms of what are called scattering cross-sections and decay rates. You take these probabilities, you convert them into the kinds of quantities you would actually measure in a particle accelerator, but they're still based on the Born rule. And you're still using the Born rule to calculate those probabilistic predictions. And usually you're doing only one measurement and then you're calling it quits. So you don't usually see the collapse anymore in the formalism. You don't collapse the quantum state and then take the collapsed quantum state and do something else on it. So the measurement problem is a little more implicit in the formalism for the most part. We call, by the way, the array, the set of all of the scattering amplitudes, the complex numbers that you then compute scattering cross-sections and decay rates out of. We call that array of all of them, that data set of all of them, we call that the S matrix. And so a lot of the time in quantum field theory, you're trying to understand the S matrix and compute, the entries in this S matrix, or trying to study its analytic mathematical properties or whatever. So the standard problems are still there, even if maybe they're a little more suppressed, given the kinds of things we usually work with in quantum field theory. Students are often surprised when they do quantum field theory that they're not using the Schrodinger equation very much anymore. So a lot of those older problems, like I said, are just less manifest. But in addition to all those problems, there are new problems that show up. Quantum field theories are phrased in a manifestly special relativistic language. And there are new kinds of problems that show up there. In particular, if you do want to think about doing multiple measurements on a quantum field theory, well, then you can't have one measurement be in the infinite past and one measurement in the infinite future, because if you want to do another measurement, you can't do something after the infinite future. You have to actually take seriously that things happen in finite amounts of time. And now you're talking about doing measurements ostensibly in some kind of space-time picture. You're thinking about your measurements being events, in some sense localized in space and in time, in a relativistic context.
If you're hungry for deeper dives into physics, AI, consciousness, philosophy, along with my personal reflections, you'll find it all on my Substack, Subscribers get first access to new episodes, new posts as well, behind-the-scenes insights, and the chance to be a part of a thriving community of like-minded pilgrimers. By joining, you'll directly be supporting my work and helping keep these conversations at the cutting edge. So click the link on screen here, hit subscribe, and let's keep pushing the boundaries of knowledge together. Thank you and enjoy the show. Just so you know, if you're listening, it's CurtJaimungal.org, CurtJaimungal.org.